Guten Tag, hallo. Jawohl, schön. Nach der Flut kommt jetzt ein schöner Vortrag von Sven Martin Hallberg und der geht darum, wie, in Englisch auch. We're gonna have a talk by Sven Martin Hallberg and it's about how the Swedes hacked the Nazis and have fun. A warm welcome, please.
Yeah, hello, okay. Yes. The talk is titled Swedish Analysis of Nazi Crypto TTYs. Crypto TTYs, means teleprinters with automatic encryption. In particular this device, it's called Siemens & Halske T52. Which is less well known than the famous Enigma, but had much stronger crypto. So, it's an electromechanical teleprinter. That means, well, you take two of these, hook them together by wires, type the keys, and it does the crypto on the wire, right? That means it's automatic. And, well, one reason why these things are less well known is they were really heavy, 100 kilograms or something. That's why there were not many of them in operation and only on high levels and for very important, like diplomatic traffic or stuff like that. Okay, here just for comparison, the Enigma, which was a pretty simple device in comparison. It consisted only of a few, the switches, a few plugs, and lamps with the which the ciphertext would appear on, and you would have to write everything manually. You know, you'd have your message, and then you would type the key, and you would write down the ciphertext yourself. This made it a very comparatively lightweight thing that was used in the field, and many of them were manufactured. So that sets it apart from this, from the T52. Also, well, cryptographically, the Enigma, some of you may know it, was a relatively simple substitution cipher by today's standards. The T52, in contrast, used something, well, it used a stream cipher as we know it today, an XOR actually, and something additional which I will get into. But so you can really compare this to, say, WEP encryption, and you can also compare the way it's cracked to WEP. So that makes it a little interesting. Okay, so for the overview of the talk, at first I'm going to explain something about the political and technical setting of the time. This is 1940s, World War II is in full swing. And well, this is going to be pretty short, only what you need to know. And then we're gonna go into how it was actually broken by the Swedish team, which includes obviously, well, deciphering some messages, then finding out what the algorithm actually is that's used by the machine, and then actually finding out the real buildup of the machine, including all the wheels and patterns and whatever it means. So the Swedes would have actually been able to build a T52 on their own. And in fact, they did something quite similar. They built things to decrypt automatically. And then I will conclude. So let's start with the setting. It's 1940. That's when this whole thing started. A situation is as follows. Germany is at this point still neutral with Russia. They had this pact. And Russia had just invaded Finland, and Germany was busy fighting the Allies in Norway, because Norway was important for the iron or something, and well, so Sweden was technically neutral but surrounded by fights. So they were eager to know what was going on, and that's why they formed a cryptanalysis division of their military, which was actually founded pretty early already, when they started breaking the T52, they had it already well set up, which was due to, well, good foresight by one of the main guys, which I'm not going to go into that much because he wasn't directly involved with the T52. But that's important, so they had already gathered lots of experience cracking other traffic from all over the place, Russian, French, English, and so on. So they were routinely intercepting radio traffic at the time already. And what they were usually breaking were codebook ciphers. That is, you have a big book that lists for every major word a certain code number, and then you would just, substitute and maybe do something else. For example, the Russians, they super enciphered, they substitute all the words, and then they would encipher the resulting text with a one-time pad. So, well, and here the key figure appears, which is a guy named Arne Bäuerling. He was head of the Russian section, decoding their super enciphered code books, and well, in the end, he ended up with the T52s. So first, for his background to the Russian code books, well, as I said, per word substitution. And then they super enciphered with one-time pads, but because the one-time pads have the problem of logistics, they just reused parts of the pads. So every message, they would just pick out one part of the pad and use that and do this over and over again. So that leads to well, when you encipher the same message with the same one-time pad, you end up having the same ciphertext in places where you have the same plain text already, right? This is called a repeat, and that's what you use in breaking it. So that's his background, and it should prove useful for the T52. So at some point in 1950, he gets a ton of, well, unusual-looking intercepts on his desk without at first knowing what they were, where they came from. He just found them on his desk and, well, looked at them. One thing that stood out was that the symbols weren't grouped. Usually, when you do hand crypto, you group the characters in groups of 5 or something, so it's easier for a human to process it. And these were just really long strings. And they used, well, 32 characters, the 26 letters and 6 digits, which, well, everyone notices it's a power of 2. So he concluded this is probably machine crypto, which was a rare thing at the time. Okay. Well, severely unreadable, that's a quote, by the way, from one of the interception guys. The Germans were initially sending the traffic in the clear, and then the machines would switch over at some point. And the guy said, well, look, our intercepts suddenly became severely unreadable. Funny way to say it. Well, by the way, they were, what I forgot to say, they were intercepting these from their own lines. The Germans had leased telegraph lines going through Sweden in order to communicate with their troops in Norway. That's how they were getting these intercepts. So they put up a listening station on their own lines and just intercepted everything. Okay, so now I'm going to go into a little bit of the technical background of that time. The teleprinters used a standardized alphabet known as Bordeaux code, or ITA2, which stands for International Teleprinter Alphabet number 2. It uses a representation of 5 bits per character, and that explains the 32 characters he was seeing in the intercepts. I'll show you a diagram in a minute. And well, because 5 bits aren't that much, they were using 2 modes. They were using 2 modes for the machines, letter and figure shift. As the name implies, letter was for letters and figures had special characters in that mode. And there was a control code that would be sent and switch the machine into the one of the two modes. Here you can see that this is a table, an abbreviated table of the teleprinter alphabet ITA2. It starts with the letters, and then you have the 5-bit representation. These were sent over 5 wires in parallel, if I recall correctly. And here at the lower part, you see the special characters, character to a new line, and here's letter shift and figure shift. These are the important ones. And well, here, this is the notation that they used in the intercepts, because so they used the digits for the special characters in order to make them visible, because in the ciphertext you couldn't tell anymore anyway. And this doesn't include the digits, so it's not ambiguous. You see. So that's why you see this strange representation where you have the normal characters and only 6 digits. So the digits in the following are always representations of the special codes. Okay. Well, teleprinter cryptography in itself was not entirely new. It was in principle known, the technique to, well, bitwise XOR the plain text with a key stream. And it was also a known idea to use a pseudo-random number generator for the key stream. And the random numbers were usually generated, this was also a known technique, by pinwheels. I'll get into the details of what that is exactly in a second. So you would have a bunch of wheels in the machine and they would turn and spit out random bits. In particular, the wheels were circumscribed with random bits, basically. The bits represented by little pins. That's why it's called a pinwheel. So you would have the little wheel, and the little pins on it, and they would be read mechanically by some kind of feeler thing in the machine, and then you would turn the wheels in order to generate a new bit. If you wanted to have multiple bits, like I said, the machines they use these 5 parallel lines for the characters. If you would want to have 5 bits at the same time, you would use 5 wheels. And well, the wheels have different numbers of bits on their circumference usually, and in fact they usually have co-prime numbers because that maximizes the period of the whole thing. If you have 5 wheels and you turn them one step for each character, then, well, at some point you will repeat the sequence of random bits, right? And, well, you maximize that if all the periods of the individual wheels have no common factors. So what you use is the least common multiple of the whole of all the individual periods, and then you get a maximum period for the entire random stream. So this was the basic technique, which was already known, teleprinter crypto. So let's see what they did with the intercepts. Yeah, first this little disclaimer. This was, well, the original T52. There were several models. Later models were a little bit harder because they improved the way the wheels worked. I just said the wheels all step in sync with every character. They changed that later, and it makes it a lot harder because they don't repeat as predictably. Well, the original one, though, did step in sync, and it was broken in just 2 weeks by him. Without him actually knowing much about this whole stuff at the time, but it's safe to assume that he kind of familiarized himself